Let us now start open map and open set related theorem. This plays an important role. Open set plays an important role and obviously a necessary thing for analysis. We discuss and we see all are open in this world. Now we discuss about this question, very important question. Let X be a matrix space. Let X be a matrix space and A belongs to X and A belongs to X. Fix R greater than 0. Fix R greater than 0. We have to show that. We have to show that. We have to show that the set X such that X belongs to X such that dxa greater than R is open. Okay, now we prove it. This one so simple. We prove it now. For x belongs to u, where u equal to x belongs to x such that dxa less than greater than r. Okay, then x belongs to u and let is equal to dxa reference r greater than 0. Let s be this. Then this figure is similarly x r. Here r. Okay, and totally this one x, this one a, so dxa. That means dxa minus r obviously greater than 0. Okay, now we choose then b x comma s. Bx comma s, that means ball center at x and radius is obviously subset of u, because b dx comma e or something is greater than r. Dx comma e greater than r, those x. Here r is greater than r. Here we see is greater than r. Okay, for this cause bxa subset of u. Okay, bxa subset of u, then x belongs to u and bxa subset of u, so u is open. So u is open. Understand or not? Just we see this figure. A contain an r radius ball and x contains a x radius ball. Okay, and here totally this to this is dxa. Dxa greater than obviously r and greater than is also, and is obviously greater than r. So bx is contain x and contain this u also. Okay, so u is open. Now we discuss further another problem related to open map and open set. Now discuss another problem, another important problem. This problem is very easy. So we just completely now start with that problem. With that problem, what is want? Here so that here let u equal to r differentiate. Each u is open in R. This one is the question mark with usual absolute value metric. Each u is open in R. Now we discuss further. Let x belongs to u equal to R differentiate. X belongs to u equal to R differentiate. Then what we obtain? We obtain given a unique integer m such that m less than x less than m plus 1. Okay, let rx equal to minimum of x minus m and m plus 1 minus x. Okay, then we see that p rx x subset of u. Here we're taking m, here is m plus 1. Now we take here x and one ball containing this x and contain this part. This is the part of R differentiate. So R differentiate is open. Okay, today we're going further procedure. So erase this portion now. We erase this portion. Then what we do, we write this next questions. This one and another important question. U equal to xy belongs to R square such that xy not equal to 0 is open in R square. Is open in R square. Okay, how we handle it? We handle it so simply. U equal to this one, xy not equal to 0. Let we choose let r equal to minimum of mod of x and mod of y. Then xy, let xy belongs to r square. Xy belongs to r square. Let xy belongs to u. Then xy belongs to r square and xy not equal to 0. So what we obtain? We obtain x belongs to Vrx and y belongs to Vry. So xy belongs to Vrx, Vry. Okay, subset of u, because xy is not 0. Here xy not 0, that means mod of this and this is not 0, and this one not contain any Vrx, and Vry does not contain 0. Where 0 does not contain Vrx and 0 does not contain Vry, then u is open set. Okay, in R square. Now we're going further proceed another problem. This problem is so easy, but we have to handle this problem. So we reach this board. Now completely this done. Now we write another questions, which is an important question. Let u such that xy belongs to R square, such that x greater than 0 and y greater than 0. Is this open? Is this open? This one is question. Now try to overcome this. We write same thing. R equal to minimum of mod of x mod of y. Then R obviously greater than 0. Okay, and let xy here given, so another point choose then better. Let AB belongs to u. This implies that AB belongs to R square and a greater than 0, b greater than 0. Now I set a belongs to V R A and B belongs to V R B. Okay, where R1 equal to minimum of mod A mod B greater than 0. Okay, then AB belongs to BR1A, BR1B, subset of U, where since A minus R1 greater than 0 and B minus R1 greater than 0, if this one possible, then If this was not possible, then this is not belonging to U. This is not subset of U. Okay, this one possible, then this one is subset of U. So U is open. That means this A and B greater than R. Okay, here open, when x greater than R, y greater than R, then this one is possible for open. Okay, when x greater than R and y greater than R, then this one is done. Now we can going to next questions. This questions is also an important questions for all. Questions: let u equal to xy belonging to R square such that x does not belongs to z and y does not belongs to z. Each u is open in R. Each u is open in R. Each u is open in R square. Okay. Then what I done? We done simply take u is given here. Now we take AB belongs to U. Let AB belongs to U and MN belongs to Z. MN belongs to Z and M less than A less than M plus 1 and N less than B less than N plus 1. Okay. Let R1 such that minimum of A minus M and M plus 1 minus A and R2 equal to minimum of B minus N and N plus 1 minus B. Okay, consider R1 and R2. Then what happened? Then we choose R equal to minimum of R1 and R2. Then what happened? Then xy belonging to Brx and Bry subset of U. Xy belonging to this Brx and Bry and Brx and Bry subset of U. That means they are not contain any integer also. Okay, so U is open, hence U is open. Because we draw here M here m plus 1, here a. Then r1 obviously less than this or less than this minimum part, that means here this one, and r2 these things n, b and n plus 1, then this one is minimum part, this one taken, and both those two, this one minimum part, then this one taken, this one is r. If r, then x, so x belongs to b, x to r, then there is no integer obviously. And so we write here again the brx and bry does not contain any integer, does not contain any integer. Okay, if this one is possible, then we are exam. If this one is possible, then if is open. Okay, now further proceed. We're going to next questions. Questions is simply u x y belongs to r square. We're going to simply further questions. We erase this portion. Question is this: u equal to xy belongs to r square such that x square plus y square not is equal to 1. Okay, then u is open in r square. We have to show that u is open in r square. How we handle it, we know about in just single term. Just this portion is added and other this dot portions are contain u. Either does this circular region x square plus y square equal to 1. So this one is open in r square. We have to prove it. How we prove it? I prove it simply. We take v equal to b001 union of xy such that dxy00 obviously greater than 1. Okay, so v is this. Then if xy belongs to u, if x, then it lies one of these subset. If xy belongs to u, then it is one of the subsets of V, then 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 xy belongs to V subset of R square. Okay, if xy belongs to U, here U and V are same, so we write here U. Okay, if xy belongs to this, it lies one of the subset of U, belong is subset of R square, then U is open. Open in R square. Okay, or otherwise you talk about if xy belongs to some any one of subset, then this one is properly contained in U, so U is open in R. Okay, this one also you write here, if xy belongs to any one of subset, if xy belongs to any one of subset, if xy belongs to any one of the subset which containing by U, so U is open in R square. Okay, so all are done. Now next, another questions is familiar questions. We erase this portion, then another questions, we're going to another questions. This questions is A be any finite set in a matrix space XT. A be any finite set in a matrix space XT, then show that X difference A is open. Write it. Let A be a finite set. A be a finite set in a matrix space XT, in a matrix space XT, then X difference A is open. So how we handle it? We handle it simply just we write A equal to AI, I equal to single AI, I equal to 1 2 dot 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 n, or in this way I equal to 1 n. Okay, but this one is not right here. So what we done, we have to see that X difference A is open. A is collection of some finite element or A be finite set. A be finite set, then take R equal to minimum of dxai. Okay, 1 less than equal to I less than equal to n, where the finite set A is, where the finite set A equal to ai such that 1 less than equal to I less than equal to n. Okay, then what we choose? We choose x belongs to brx, subset of x difference a. If x belongs to x difference a, let we choose x belongs to x difference a, then x belongs to brx, subset of x difference a, and those brx is contain are equal to minimum of this x and ai's difference. So hence x difference a is open. But how it can be possible? Just a finite set contain 1 2 3 in this way, a1 a2 a3 in this way, and x does not belongs to a are those x is here. Okay, then dxai minimum is r, here minimum this one equal to r. Okay, now x belongs to br